Hello, this is the section 4.9 lesson. The first part of doing a statistical study is determining the necessary sample size. In this section we're going to look at a couple of simple techniques for doing so. Let's start off with a scenario where we'd like to estimate the population proportion of candidates, of voters who support a particular political candidate. So suppose we go out and we survey 785 voters and find that 395 of them support this candidate. And so our sample proportion p hat is the 395 divided by 758, which is 0.521. So that means that about 52% of the voters support this particular candidate. Okay. Well, we could calculate the margin of error in that estimate. So if we use a 95% confidence level, our margin of error is given by this formula here from a couple of sections ago, and we plug in our numbers. Our critical value is 1.96. We do that arithmetic and we get a margin of error of 0.0349. So what that means is that our estimate of P, the population proportion of voters who support this particular candidate, is an error by as much as 3.5 percentage points at the 95% confidence level. So a pundit may say, well, okay, that's a fine estimate, but suppose we want to do better. I would like a better estimate with a smaller margin of error. And so we're going to have to survey more voters to get a better estimate. But the question is, how many more voters do we need to survey? Do we need just 50 more voters? Do we need 500? Do we need 5,000? Just how many more do we need? Well, we're going to have to be a little bit more specific in our question. But let's start looking at the theory behind how we could calculate this. So our margin of error, formula for margin of error, is given by this simple formula here. And if we do a little bit of algebraic manipulation to solve this for n, we come up with this. So to go from here to here, we simply squared both sides, divided by z, rearranged to get n, just a little bit of high school algebra. And so that leads to our formula for the necessary sample size when trying to estimate a population proportion. N is z squared times p hat times 1 minus p hat divided by e squared. Now, z sub alpha divided by 2, that's our critical z value at the desired confidence level. P hat is an estimate of the population proportion. And then e is our desired margin of error. Now, one thing we should note here about this formula is that the population size doesn't affect anything. And in fact, as long as the population size n is large, the exact value of n does not matter. Now, by large, what we really mean is that the sample size is less than 5% of the population size. And so if that's a reasonable assumption, then the exact population size just does not matter. Now, the case of a small population size is dealt with in one of the exercises. Now, to use this formula, we need an estimate of P, the population proportion. And there are at least three ways that we could come up with an estimate. Number one is to use an estimate from a previous survey. And that's exactly what we have here. We've already done a survey. We just want to kind of improve on it. And so we're going to use our estimate of P from that first survey. Number two, we could use knowledge of the circumstances. Maybe in this scenario we may say, well, based off of anecdotal evidence, maybe I think 55% of voters support this candidate. So I could use 0.55 as my value of p hat. Third case, if completely unknown, then we'll just use p hat equals 0.5. Now, why 0.5? Well, there's a couple of reasons. One of them is that p is somewhere between 0 and 1. And so we could just take the number right in the middle as an estimate, 0.5. Another reason for choosing p hat equals 0.5 is discussed in the exercises. And so let's go back to our example and state our question in a little more formal terms. How many voters must be surveyed so the margin of error for estimating p is no more than 0.025 at the 95% confidence level? Okay. Now, where did this number 0.025 come from? Well, that's just a desired margin of error. Remember, our original margin of error was about 0.035. we want to do better, so we'll choose a smaller margin of error. So in other words, we want a margin of error E to be 0.025, and in our formula for N, we're going to use P hat to be the sample proportion from the previous study, 0.521. And so now it's just a matter of plugging stuff into our formula. We need our critical value. We're told to use a 95% confidence level, and so our critical value is 1.96. Square that times P hat, 1 minus P hat divided by E squared. And we do that arithmetic, and the final answer that we get, we're always going to round up to the next whole number. Remember, sample size has to be a whole number, and a bigger sample size is better than smaller, so we're always going to round it up. So there, that tells us we need a total of about 1,534 voters. So remember, we had already surveyed 758 voters. So if we subtract that from the 1,500 we need, we see that we need to survey about 776 more voters. So in other words, we need to roughly double our sample size to get this smaller desired margin of error. Now, when estimating a population mean, we can calculate a sample size in a very similar fashion. So remember, for estimating a population mean, we had two different types of confidence intervals. We had a Z interval and then a T interval. Well, we're going to talk about the Z interval here, and the formula for the margin of error was given by this. We had our critical z-score. Sigma was our known population population standard deviation, and then N was our desired sample size. And so if we do a little bit of algebraic manipulation, we solve that for N, we get this result. And so that leads us to our formula for the necessary sample size when estimating a population mean. So again, we have our critical z value, and we have sigma here, and so sigma, or sigma squared, is an estimate of the population variance. And then E is our desired margin of error. So a very similar looking formula to what we had for the population proportion. And now again, note that the population size doesn't appear in this formula, and so as long as the population size is relatively large relative to N, then the exact value of N just doesn't matter. So N could be 5,000, 50,000, 5 million, 5 billion. It just doesn't matter. All that matters here in our value of N is the Z value, which is affected by the confidence level. We have sigma squared, our estimate of the population variance, and then E, our desired margin of error. And so again, the exact population size just doesn't matter as long as it's large. Now, in order to use this formula, we need an estimate of sigma, the population standard deviation. And we could get this from at least 3 different ways. Number 1, use estimate from a previous survey. Or number 2, use knowledge of the circumstances. Or a third way is to use this simple crude method for estimating the value of sigma. And in this we could take the largest possible data value minus the smallest possible data value and divide by 4. So we just think about the scenario and think, what's the largest possible value I could collect? What's the smallest possible value I could collect? Subtract them, divide by 4, and that's going to give me a very rough estimate of sigma. The logic behind this goes back to the empirical rule, which said that most data values, or most values of a random variable, are within 2 standard deviations of its mean. And so that's the basic idea there behind this formula. So to apply this to an example, suppose that a student would like to estimate the mean IQ score of all statistics professors. And so we need to figure out how many professors do we need to survey. Well, specifically, how many professors must be surveyed so the margin of error is no more than 3 units at the 90% confidence level. Now, where did the 3 units come from? Well, that's just a number that we picked out of the air. That was our desired margin of error. And so again, E is 3, and we're working at the 90% confidence level. So now we just need to plug things into our formula. Actually, before we do that, we need an estimate of sigma, our population standard deviation. Well, in the general population of people, IQ scores are standardized so that they have a standard deviation of 15. And so we'll take that population standard deviation from the larger population as an estimate of the standard deviation in our smaller population of statistics professors. Now, whether that's a reasonable assumption or not is maybe a little bit debatable, and the validity of that assumption and its consequences are discussed in one of the exercises. So now we're ready to plug things into our formula. Here's our formula. We need the critical z-score at a 90% confidence level, get 1.645, square that times 15 squared divided by 3 squared. We do that arithmetic, and again we always round that number up to the next whole number. So this tells us that we need to survey about 68 statistics professors.